What does the void feel like? Imagine reaching out into the universe and feeling the temperature of nothingness itself. Everything you learned about temperature is useless in space. The void operates on rules that shouldn't exist. Space is both the coldest and hottest place in the universe. Let me prove it. If you love exploring the mysteries of the universe, please hit that subscribe button. You'll be joining a community of curious minds. Now let's get started. Let's talk about cold. On Earth, if you step outside on a -40-degree day, you'll freeze quickly because the air molecules constantly bombard your body, stealing your heat through conduction and convection. But space is different. There's no air, no molecules to carry heat away from you. If you were suddenly exposed to the vacuum of space, and this is going to sound counterintuitive, you wouldn't freeze instantly. In fact, freezing would be one of your last problems. You'd face much more immediate dangers. Your body would start to swell as the water in your tissues began to vaporize. The moisture on your tongue, your eyes, your lungs would boil. Not because space is hot, but because liquids boil at much lower temperatures when pressure drops. This is what we talked about in my video, the real reason we will never survive deep space, on the card above, where we explored the brutal reality of what space does to unprotected human bodies. The physics is unforgiving, but understanding it helps us appreciate just how remarkable our engineering achievements are in keeping astronauts safe. The link to the video is in the description. But back to temperature. The reason you wouldn't freeze instantly is because in a vacuum, the only way to lose heat is through radiation. Your body radiates infrared light, slowly releasing energy into the void. This process takes time, much more time than freezing in cold air. NASA studies on vacuum exposure in the 1960s and 70s showed that animals could survive brief exposures to vacuum, not because vacuum is safe, but because heat loss through radiation alone is surprisingly slow. This brings us to one of the most fascinating temperature paradoxes in space. If you were floating in the shadow of Earth, shielded from the sun, you'd eventually freeze as your body radiated heat away. But if you were in direct sunlight, you'd actually overheat. The sun's radiation would warm one side of your body to over 120 degrees Celsius, while the other side slowly cooled. Space isn't uniformly cold. It's a place of extreme temperature contrasts. This is why spacecraft design is so challenging. Engineers have to deal with temperature swings that would destroy most materials. The International Space Station, orbiting just 400 kilometers above Earth, experiences temperature variations from -150 degrees Celsius in shadow to 120 degrees Celsius in sunlight every 90 minutes as it circles our planet. That's a temperature range of 270 degrees, cycling continuously. The materials, the electronics, the life support systems, everything has to withstand these brutal extremes. Let's talk about how we actually measure the temperature of space. You can't just stick a thermometer out the window of your spacecraft and get a reading. Why? Because a thermometer measures the kinetic energy of molecules bouncing against it. In the near-perfect vacuum of space, there are so few molecules that a regular thermometer would tell you almost nothing useful. Instead, scientists measure the radiation environment, the photons streaming through space from various sources, the James Webb Space Telescope, humanity's most powerful infrared observatory, launched on December 25, 2021, gives us a perfect example of how spacecraft deal with the cold of space. Webb observes the universe in infrared light, which means it's essentially looking at heat signatures from distant galaxies. But here's the problem. If the telescope itself is warm, its own heat would overwhelm the faint signals it's trying to detect. It would be like trying to see distant stars through the glare of a spotlight pointed at your face. So engineers designed one of the most extraordinary thermal systems ever created. Webb has a sun shield the size of a tennis court, 5 layers of material thinner than a human hair, each one coated with reflective aluminum and doped silicon. This sun shield creates temperature difference of approximately 299 degrees Celsius between its hot side and cold side. The sun-facing side reaches about 85 degrees Celsius, hot enough to boil water at low pressure. But the cold side, where the telescope sits, drops to around minus 233 degrees Celsius, just 40 degrees above absolute zero. This temperature is actually colder than the natural background temperature of space. Webb uses the cold of space, enhanced by its brilliant engineering, to become one of the coldest objects in the inner solar system. The telescope's instruments operate at even lower temperatures. The mid-infrared instrument, MIRI, uses an active cryocooler system to drop its temperature to minus 266 degrees Celsius, just 7 Kelvin above absolute zero. At these temperatures, atoms barely move. Molecular vibrations nearly cease. It's about as close to perfect stillness as matter can achieve. Think about what this means. We've built a machine that operates colder than the cosmic microwave background radiation itself. We're using technology to out-cold the natural coldness of the universe. That's not just engineering, that's poetry written in aluminum and physics. But temperature in space varies wildly, depending on where you are and what's around you. Near Earth, in low orbit, you have the planet below radiating infrared heat, the sun blazing above, and the reflected sunlight bouncing off Earth's clouds and oceans. An object in low Earth orbit exists in a complex thermal environment with multiple heat sources. Move out to the moon and things change. With no atmosphere to scatter sunlight or retain heat, the lunar surface experiences temperature swings from 127 degrees Celsius in direct sunlight to minus 173 degrees Celsius in shadow. That's a 300-degree temperature range, and it happens relatively quickly when the sun sets over the lunar horizon. The Apollo astronauts who walked on the moon between 1969 and 1972 experienced these extremes firsthand. Their spacesuits had to handle both the scorching heat of lunar day and the bitter cold of shadows. The suits used multiple layers of insulation, reflective surfaces, and even liquid cooling systems to keep the astronauts comfortable. Inside those suits, temperatures stayed around 21 degrees Celsius, a comfortable room temperature, while outside, the surface baked or froze, travel farther from the sun, and things get progressively colder. Mars, at 1.5 times Earth's distance from the sun, has an average temperature of minus 63 degrees Celsius. But that's just an average. At the equator during summer, temperatures can reach a pleasant 20 degrees Celsius in the afternoon, then plummet to minus 73 degrees Celsius at night. The thin atmosphere, less than 1% the density of Earth's, provides almost no insulation. Heat radiates away rapidly once the sun sets. The outer planets exist in a realm of perpetual deep freeze. Jupiter, at 5.2 astronomical units from the sun, has cloud-top temperatures around minus 145 degrees Celsius. Saturn, nearly twice as far, is even colder at -178 degrees Celsius. Uranus and Neptune, the ice giants lurking at the edge of the planetary system, have atmospheric temperatures dropping below -200 degrees Celsius. Yet even these frigid worlds aren't as cold as interstellar space itself, because they have internal heat sources, energy left over from their formation, or generated by the slow compression of their cores. This raises a fascinating question. What's the coldest natural place in the universe? You might think it's the depths of intergalactic space, far from any stars or galaxies. And you'd be close, but not quite right. The Boomerang Nebula, a dying star about 5,000 light-years from Earth in the constellation Centaurus, holds the record for the coldest known natural place in the universe. Its temperature is measured at 1 Kelvin, -272.15 degrees Celsius. That's colder than the cosmic microwave background itself. How is this possible? How can something be colder than the background temperature of space? The answer lies in a beautiful piece of physics called adiabatic expansion. The dying star at the center of the Boomerang Nebula is expelling gas at tremendous speeds, around 640,000 kilometers per hour. As this gas expands into space, it does work against the surrounding material, and in doing so, it cools. The expansion happens so rapidly that the gas cools faster than it can absorb heat from the cosmic microwave background radiation. It's like a cosmic refrigerator, using the energy of expansion to create temperatures colder than nature's baseline. Scientists discovered the Boomerang Nebula's extreme cold in 1995 using ground-based telescopes, then confirmed it with observations from the Hubble Space Telescope and the ALMA Observatory in Chile. The nebula appears blue in optical light because of how it scatters starlight, and its unusual hourglass shape tells us we're seeing something remarkable, a star in its final death throes, creating a monument of cold in the warm universe. This discovery changed how we think about temperature in space. It showed us that local conditions can create temperatures that defy the cosmic average. The universe isn't uniformly 2.7 Kelvin everywhere. The cooling of the universe isn't just ancient history. It's happening right now, all around you. Every second, the cosmic microwave background gets infinitesimally colder as space stretches. In 1 billion years from now, the temperature of space will have dropped to about 2.69 Kelvin. It doesn't sound like much, but this gradual cooling is one of the fundamental processes shaping the fate of our universe. Eventually, trillions upon trillions of years in the future, the universe will approach a temperature asymptotically close to absolute zero, though it will never quite reach it. This is the heat death scenario, where all usable energy has been exhausted and the cosmos reaches maximum entropy. But we're getting ahead of ourselves. Let's come back to the present and talk about something that seems simple, but is actually deeply strange. What does cold mean in the context of space? On Earth, cold is something you feel. It's the sensation of heat leaving your body. But sensation requires nerves, biological systems that evolved in Earth's atmosphere. In space, there's no medium to conduct heat away from you rapidly, so the concept of feeling cold becomes abstract. You wouldn't feel the 2.7 Kelvin temperature of space touching your skin because there's nothing there to touch you. This is why the concept of temperature in a vacuum is fundamentally different from temperature in matter. Temperature in matter measures how fast molecules are jiggling around. In a gas, it measures average kinetic energy. In a solid, it measures vibrational energy in the crystal lattice. But in the vacuum of space, temperature measures the energy of the radiation field, the photons streaming through emptiness. These are completely different physical phenomena that we describe with the same word, temperature, because they follow similar mathematical laws. Physicists use something called the radiation temperature or brightness temperature to describe space. This is the temperature that a perfect black body would need to have to emit the radiation we observe. The cosmic microwave background has a brightness temperature of 2.725 Kelvin because it looks exactly like the radiation that would be emitted by a perfect blackbody at that temperature. It's one of the most perfect blackbody spectra ever measured, so perfect that it convinced scientists the Big Bang theory was correct. When Arno Penzias and Robert Wilson accidentally discovered the cosmic microwave background in 1964, they were just trying to eliminate noise from their radio antenna. They kept detecting this persistent hiss, this background static that came from every direction in the sky. They cleaned pigeon droppings off their antenna. They checked every electronic component, but the signal remained. What they'd found was the echo of creation itself, the cooled remnant of the Big Bang, and it earned them the Nobel Prize in Physics in 1978. Their initial measurement put the temperature at around 3.5 Kelvin, which was remarkably close considering the primitive equipment they used. Later, more sophisticated measurements refined this number. The COBE satellite in the 1990s, WMAP in the 2000s, and the Planck satellite from 2009 to 2013 gave us increasingly precise measurements. Today, we know the temperature of the cosmic microwave background to 5 significant figures. That's extraordinary precision for measuring something that fills the entire universe. But here's something that makes this even more fascinating. The temperature of space isn't completely uniform. There are tiny variations, hot spots and cold spots, that differ from the average by only about 1 part in 100,000. These temperature fluctuations, called anisotropies, are incredibly important. They're the fingerprints of quantum fluctuations from the first fraction of a second after the Big Bang, inflated to cosmic scales by a period of exponential expansion we call cosmic inflation. The pattern of these temperature variations tells us about the geometry of the universe, the amount of dark matter and dark energy, and the conditions in the first moments of cosmic time. Scientists can analyze the pattern like a musical chord, breaking it down into different frequencies and amplitudes. What they find is a universe that's geometrically flat, composed of about 5% ordinary matter, 27% dark matter, and 68% dark energy. All of this information is encoded in tiny temperature variations in the coldness of space. Think about that. The temperature of nothingness contains the entire history and composition of everything. The cold of space is not empty. It's full of information, full of meaning, full of the story of how we came to be. When you look up at the night sky, you're not seeing darkness, you're seeing ancient light, cooled by expansion, carrying messages from the birth of time. Now, let's talk about something practical. If we want to explore space, if we want to send humans to Mars, to the moons of Jupiter or beyond, we need to understand not just how cold space is, but how to survive in that cold. The challenge isn't just keeping astronauts warm. It's managing heat in an environment where normal heat transfer doesn't work the way we're used to. On Earth, If a machine overheats, you can cool it with a fan or water cooling system. Both methods rely on transferring heat to a medium, air or water, which then carries that heat away. In space, there's no medium. You can't use a fan because there's no air. You can't vent heat into space the way you'd vent it into the atmosphere. The only way to get rid of excess heat is through thermal radiation, emitting infrared light into space. This is why spacecraft have radiators, large panels designed to maximize surface area and radiate heat into space. The International Space Station has massive radiator panels that glow in infrared as they dump waste heat from the station's systems. These radiators are critical. Without them, the electronics, the life support systems, and the astronauts themselves would overheat despite being surrounded by the cold of space. It's a counterintuitive problem that requires elegant engineering solutions. The Mars rovers, Spirit, Opportunity, Curiosity, and Perseverance face a different challenge. Mars has an atmosphere, thin as it is, which means there's some convective heat transfer. But Martian nights are brutally cold, often dropping below -90 degrees Celsius. The rovers use radioisotope thermoelectric generators, essentially nuclear batteries, to stay warm. These devices convert heat from decaying plutonium into electricity and use the waste heat to keep sensitive electronics above their minimum operating temperatures. Perseverance, which landed in Jezero crater on February 18, 2021, carries the most sophisticated thermal system ever sent to Mars. It has heat exchangers, insulation, heaters, and a complex system of fluid loops to move heat around. During the Martian day, when temperatures might reach -20 degrees Celsius at the equator, the rover has to prevent overheating. At night, when temperatures plummet, it has to conserve every bit of warmth. It's a constant balancing act, managing energy and temperature to keep the rover alive and functional. But Mars is practically tropical compared to the outer solar system. When NASA's Cassini spacecraft orbited Saturn from 2004 to 2017, it operated in an environment where sunlight is 100 times dimmer than at Earth. Solar panels wouldn't provide enough power, so Cassini used radioisotope generators like the Mars rovers. But the cold at Saturn, where temperatures drop below -180 degrees Celsius, presented unique challenges. Some of Cassini's systems actually benefited from the cold. Its electronics ran more efficiently at low temperatures, but other systems, particularly the propellant in its thrusters, had to be kept warm enough to remain liquid. Engineers designed a thermal control system that used the waste heat from the radioisotope generators strategically, routing it through the spacecraft to keep critical systems within their operating ranges. For 13 years, this delicate thermal dance continued until Cassini's final plunge into Saturn's atmosphere on September 15, 2017. Even more extreme is the New Horizons spacecraft, which flew past Pluto on July 14, 2015, and continues journeying into the Kuiper Belt. At Pluto's distance, nearly 40 times farther from the Sun than Earth, sunlight is almost non-existent. The spacecraft operates in a realm where temperatures hover around -230 degrees Celsius. New Horizons uses a radioisotope generator not primarily for power, but for heat. The plutonium core generates about 200 watts of thermal energy, and every watt is precious for keeping the spacecraft's electronics from freezing solid. The spacecraft is wrapped in multi-layer insulation, blankets of reflective material separated by vacuum gaps, the same principle that keeps your coffee hot in a thermos bottle. These blankets minimize heat loss through radiation, trapping warmth close to the spacecraft's body. It's remarkable when you think about it. We're using the principles of keeping things warm to protect our technology in an environment that's only about 40 degrees warmer than the coldest temperature in the entire universe. Now, let's consider something truly mind-bending. We've talked about how cold space is, but what about the coldest temperature possible? Absolute zero, 0 Kelvin, minus 273.15 degrees Celsius is the theoretical limit where all molecular motion ceases. At absolute zero, atoms would occupy their lowest possible energy states. Quantum mechanics tells us that even at absolute zero, there's still some residual energy called zero-point energy, but for all practical purposes, absolute zero represents the bottom of the temperature scale. Here's the fascinating part. You cannot actually reach absolute zero. The third law of thermodynamics states that it's impossible to cool any system to absolute zero in a finite number of steps. You can get arbitrarily close, infinitesimally close, but never quite there. It's like an asymptote in mathematics, a line you approach but never touch. Scientists have cooled atoms to billionths of a Kelvin above absolute zero in laboratory experiments, creating exotic states of matter like Bose-Einstein condensates, where atoms lose their individual identities and behave as a single quantum entity. But even these incredible achievements can't quite reach the ultimate cold. Why does this limit exist? It comes down to quantum mechanics and the Heisenberg uncertainty principle. If you could cool something to absolute zero, you'd know both its position and momentum with perfect precision, which quantum mechanics forbids. The universe has fundamental limits built into its fabric, and absolute zero is one of them. Space, at 2.725 Kelvin, is cold, incredibly cold, but it's still separated from absolute zero by a gulf that can never be completely crossed. This brings us to a profound realization. The coldness of space, that 2.7 Kelvin background, is not just a random number. It's a consequence of the universe's expansion and age. If the universe were younger, space would be warmer. If it were older, space would be colder. The temperature of space is, in a very real sense, a thermometer measuring the age and expansion rate of the cosmos. When cosmologists measure the cosmic microwave background temperature with extreme precision, they're measuring time itself, the time since the Big Bang, encoded in the energy of ancient photons. Let's shift perspective and think about what happens in the coldest regions of space, the molecular clouds where new stars are born. These vast clouds of gas and dust, stretching for dozens of light years, have temperatures as low as 10 Kelvin, just 7 degrees above the cosmic background. At these temperatures, molecules move sluggishly. Hydrogen, the most abundant element in the universe, exists mostly as molecular hydrogen, two atoms bonded together. Other molecules form carbon monoxide, water, ammonia, even complex organic compounds. The cold is essential for star formation. Gravity tries to pull these clouds together, but thermal energy, the random motion of molecules, resists collapse. Only when clouds are cold enough, when molecular motions slow sufficiently, can gravity win. Dense regions within the cloud begin to collapse, heating up as gravitational potential energy converts to kinetic energy. A protostar ignites. The cold gives birth to heat, and a new sun blazes in the darkness. The Orion Nebula, one of the most spectacular star-forming regions visible from Earth, located about 1,340 light-years away, shows this process in action. Within its glowing clouds, temperatures range from a few tens of Kelvin in the outer regions to thousands of Kelvin near newly formed stars. You can see the entire temperature spectrum of stellar birth in a single object, from the cold molecular clouds to the hot ionized gas surrounding young, massive stars. It's a cosmic laboratory displaying the interplay between cold and heat, between gravity and pressure, between creation and destruction. The coldest gas in these clouds can only be detected with radio telescopes, instruments like the Atacama Large Millimeter Array, ALMA, in Chile. ALMA observes the universe at wavelengths of about 1 millimeter to 1 centimeter, perfect for detecting the faint radiation emitted by cold molecules. What ALMA has revealed is astonishing, intricate structures in molecular clouds, spirals and filaments where stars are forming, planet-forming disks around young stars with gaps and rings indicating the presence of newborn planets. All of this hidden in the cold regions that optical telescopes cannot see. Temperature in space also determines what kinds of chemistry can occur. In the warm inner regions of a protoplanetary disk close to the young star, only refractory materials can exist: metals, silicates, compounds that can withstand high temperatures. This is where rocky planets like Earth form. Farther out, beyond the snow line where temperatures drop below the freezing point of water, ice becomes stable. Here, giant planets can form, accumulating vast atmospheres of hydrogen and helium around cores of ice and rock. Our own solar system's architecture reflects this temperature gradient. Mercury, Venus, Earth, and Mars are rocky worlds formed in the warm inner region. Jupiter, Saturn, Uranus, and Neptune are ice and gas giants, formed beyond the snow line where water ice could exist. The Kuiper Belt and Oort cloud, the icy reservoirs of comets at the solar system's edge, exist in the deep cold where temperatures barely rise above the cosmic background. Every object's composition tells a story about the temperature conditions where it formed 4.6 billion years ago. Comets are particularly fascinating because they're time capsules from the early solar system. These dirty snowballs spent billions of years in the frigid outer regions, preserved in the deep freeze of space. When a comet falls toward the inner solar system and approaches the Sun, it heats up. Ice sublimes directly from solid to gas, creating the spectacular coma and tail we see from Earth. Scientists study comets because they contain pristine material from the solar system's formation, organic molecules and water that have been preserved at temperatures close to the cosmic background for eons. The Rosetta mission, which orbited Comet 67 P. Churyumov-Gerasimenko from 2014 to 2016, measured surface temperatures ranging from -180 degrees Celsius in shadowed regions to -70 degrees Celsius in sunlight, even when the comet was relatively close to the Sun. The Philae lander, which touched down on the comet's surface on November 12, 2014, detected complex organic molecules in material that had been frozen for billions of years. This is chemistry preserved by cold molecules that would have broken apart in warmer environments. Now, let's explore one of the most counterintuitive aspects of temperature in space: how it relates to nothing at all. Physicists have discovered that even the purest vacuum, empty space with absolutely nothing in it, isn't truly empty. Quantum field theory tells us that the vacuum seethes with virtual particles, particle-antiparticle pairs that pop into existence and annihilate each other in timescales so short they don't violate conservation of energy. This quantum foam, as it's sometimes called, gives the vacuum an inherent energy density. This vacuum energy has temperature implications. In 1948, Dutch physicist Hendrik Casimir predicted that two uncharged metal plates placed very close together in a vacuum would experience an attractive force. This happens because the vacuum between the plates can only support certain quantum fluctuations based on the plate separation, while the vacuum outside the plates has no such restriction. The difference in quantum vacuum energy creates a measurable force. This Casimir effect has been experimentally verified, proving that empty space itself has structure and energy. But here's where it gets wild. If vacuum has energy, does it have temperature? Stephen Hawking showed in 1974 that black holes emit thermal radiation due to quantum effects near the event horizon. This Hawking radiation has a temperature inversely proportional to the black hole's mass. A stellar mass black hole, say 10 times the mass of the Sun, would have a temperature of about 6 billionths of a Kelvin, far colder than the cosmic microwave background. But a tiny primordial black hole, if such things exist, could be much hotter, even hot enough to glow and eventually evaporate in a burst of radiation. Hawking's discovery connected thermodynamics, quantum mechanics, and gravity in a profound way. It suggested that black holes are not completely black, that they have entropy and temperature, and that information about what falls into them might eventually be returned to the universe. This sparked debates that continue today about the nature of information, entropy, and the ultimate fate of matter. All of this emerged from thinking carefully about temperature in the most extreme environments imaginable. The universe's largest structures also have temperatures we can measure. Galaxy clusters, the most massive gravitationally bound structures in the cosmos, contain thousands of galaxies embedded in vast clouds of hot gas. This intracluster medium has temperatures of tens of millions of Kelvin, so hot that it glows in X-rays. The Chandra X-ray Observatory and XMM Newton telescope have mapped this hot gas in exquisite detail, revealing shocks, bubbles, and complex flows driven by supermassive black holes at the centers of cluster galaxies. How can something in space be millions of degrees hot when the background temperature is only 2.7 Kelvin? The answer is gravity. When matter falls into a galaxy cluster, it accelerates, and when it crashes into other infalling material, kinetic energy converts to heat. The gas becomes so hot that atoms are completely ionized, stripped of all their electrons. This plasma radiates X-rays, losing energy, but the continuous infall of more matter keeps the temperature high. It's a cosmic furnace powered by gravity, heating gas to temperatures rivaling the cores of stars. The Coma cluster, about 320 million light-years from Earth, contains over 1,000 galaxies and is filled with gas at about 88 million Kelvin. That's 5 times hotter than the Sun's core. Yet this furnace sits in the cold expanse of space, surrounded by the 2.7 Kelvin background. The contrast is staggering. Temperature in the universe spans at least 13 orders of magnitude, from fractions of a Kelvin in the Boomerang Nebula to hundreds of millions of degrees in galaxy clusters, and even higher in more extreme environments. The hottest natural temperatures in the universe occur in the most violent events: supernova explosions and the collisions of neutron stars. When a massive star explodes as a supernova, the core collapses and rebounds, sending a shock wave through the star's outer layers. Temperatures in the shock reach billions of Kelvin, hot enough for nuclear fusion to create heavy elements like gold, platinum, and uranium. These elements, forged in heat unimaginable, eventually spread through space and cooled to the background temperature, becoming part of new molecular clouds, new stars, new planets. The gold in your jewelry was once billions of degrees hot, created in a stellar explosion, and has spent billions of years cooling in the cold of space. Neutron star collisions create even more extreme conditions. On August 17, 2017, the LIGO and Virgo gravitational wave detectors observed the merger of two neutron stars about 130 million light-years away. The collision created temperatures exceeding 10 billion Kelvin and produced a kilonova, an explosion that synthesized massive amounts of heavy elements. Telescopes around the world and in space observed the aftermath across the electromagnetic spectrum, from gamma rays to radio waves. It was one of the most comprehensively studied cosmic events in history, and it showed us matter and energy at temperature extremes that dwarf anything we can create on Earth. Humans have tried to recreate these conditions. The Large Hadron Collider at CERN, when it smashes heavy ions together, creates tiny fireballs of quark-gluon plasma. With temperatures around 5 trillion Kelvin, the hottest temperatures ever achieved anywhere in the universe since the Big Bang itself. These temperatures last for only tiny fractions of a second before the plasma cools and forms ordinary particles. But in those brief moments, physicists glimpse conditions that existed throughout the universe when it was only microseconds old. The temperature history of the universe is a story of cooling. At the moment of the Big Bang, temperatures were effectively infinite. As the universe expanded, it cooled. At 1 billionth of a second old, the temperature was about 10 trillion Kelvin, hot enough that quarks and gluons existed as free particles. By 1 microsecond, it had cooled to 1 trillion Kelvin, and quarks bound together to form protons and neutrons. At 1 second old, the universe was about 10 billion Kelvin, cool enough for these nuclear particles to exist stably, though still too hot for atoms. For 3 minutes after the Big Bang, nuclear fusion occurred throughout the universe, creating helium and trace amounts of lithium from primordial hydrogen. This is Big Bang nucleosynthesis, and it happened when the universe was between 1 billion and 100 million Kelvin. Then expansion diluted and cooled everything too much for fusion to continue. The universe coasted for 380,000 years, cooling gradually until temperatures dropped to 3,000 Kelvin. At that moment, electrons and nuclei combined to form the first atoms, and the universe became transparent to light. That light, the cosmic microwave background, has been traveling through space ever since, cooling as the universe expands. Until today, it has a temperature of 2.725 Kelvin. Every cubic centimeter of space contains about 400 photons from this ancient light, invisible to our eyes but detectable with radio telescopes. You're surrounded by them right now. They pass through your body by the billions every second. These ancient messengers carrying information about creation, cooled by 13.8 billion years of cosmic expansion. Understanding the temperature of space connects us to the deepest questions in physics. Why did the universe start hot and cool down? Why does entropy increase over time? What is the ultimate fate of all matter and energy? These questions don't have simple answers, but they all relate to temperature, to energy, to the fundamental laws governing how systems evolve over time. The second law of thermodynamics tells us that entropy disorder always increases in a closed system. The universe as a whole is expanding and cooling, increasing in entropy. Eventually, in the unimaginably distant future, all stars will burn out. Black holes will evaporate through Hawking radiation. Matter will decay or fall into black holes that themselves eventually disappear. The universe will approach a state of maximum entropy, with temperature approaching absolute zero. This heat death scenario represents the ultimate triumph of cold over heat, of disorder over order. But that fate lies so far in the future that the numbers become almost meaningless. We're talking about timescales of 10 to the power of 100 years or more, vastly longer than the current age of the universe. For now, and for countless eons to come, the universe remains a vibrant place where temperature gradients drive complexity, where hot and cold interact to create structure, life, and beauty. Let's bring this back to something more immediate. What would actually happen to a human body exposed to the cold of space? Science fiction often gets this dramatically wrong, showing people freezing instantly into ice sculptures or exploding from decompression. The reality is both less theatrical and more fascinating. If you were suddenly exposed to space without a suit, the first problem wouldn't be the cold at all. It would be the lack of pressure. Your body is accustomed to atmospheric pressure, about 100,000 pascals, pushing on every square centimeter of your skin. In space, that pressure drops to essentially zero. The air in your lungs would immediately expand and be expelled. You'd lose consciousness within about 15 seconds as oxygen stopped reaching your brain. But you wouldn't freeze instantly. Remember, space is a vacuum, and vacuums are excellent insulators. There's no air to conduct heat away from your body. Your body generates heat through metabolism, about 100 watts of thermal power. In the vacuum of space, you can only lose this heat through thermal radiation, which happens relatively slowly. You'd lose perhaps 1 to 2 degrees Celsius per hour initially. The moisture on your eyes, mouth, and airways would evaporate rapidly due to the low pressure, causing severe cooling in those areas. Your skin might puff up slightly as dissolved gases in your blood come out of solution. But actual freezing would take many hours. You'd die from asphyxiation and other effects of vacuum exposure long before the cold killed you. This morbid thought experiment illustrates an important point about space. The danger isn't primarily the temperature, it's the environment as a whole. Radiation, vacuum, lack of oxygen, these are the immediate threats. Temperature becomes a problem over longer timescales, which is why spacecraft need thermal control systems, but can take hours or days to reach equilibrium temperatures after their heaters fail. The Apollo 13 mission in April 1970 provides a real-world example. When an oxygen tank exploded, the crew had to shut down most of the command module's systems to conserve power. The spacecraft began cooling toward the temperature of space. But even with minimal heating and in the cold of cislunar space, temperatures inside the spacecraft only dropped to about 3 degrees Celsius over several days. It was uncomfortable, even dangerous for the crew, but not instantly fatal. The insulation provided by the spacecraft's structure and the residual heat from electronics and the astronauts themselves kept the temperature above freezing. This resilience comes from the same physics that makes space a good insulator. With no air to conduct heat away, thermal radiation becomes the primary heat transfer mechanism, and radiation is relatively slow. That's why a thermos bottle works. It creates a vacuum between two reflective walls, minimizing both conduction and radiation. Spacecraft are essentially very sophisticated thermos bottles, designed to maintain habitable temperatures in an environment that's either blazingly hot when facing the sun or incredibly cold when in shadow. Temperature management becomes even more critical for long-duration space missions. The International Space Station has been continuously occupied since November 2nd, 2000, making it humanity's longest-running experiment in living off Earth. The station orbits about 400 kilometers above Earth's surface, completing one orbit every 90 minutes. During each orbit, it spends about 45 minutes in sunlight and 45 minutes in Earth's shadow. The temperature swings are dramatic. The sun-facing side can reach 121 degrees Celsius, while the shadowed side drops to -157 degrees Celsius. Managing these temperature swings requires an intricate thermal control system. The station uses a combination of passive and active systems. Passive systems include multi-layer insulation blankets, reflective surfaces, and thermal coatings that either absorb or reflect heat depending on their location. Active systems include pumps, circulating ammonia through external radiators, heat exchangers transferring heat from interior water loops to the external ammonia loops, and heaters that activate when temperatures drop too low. The station's radiators are particularly impressive. These large white panels extend from the station's truss structure and can be rotated to control how much heat they radiate into space. When the station generates excess heat, the radiators orient edge onto the sun, maximizing their surface area for radiating heat into space. When conservation of heat is needed, they rotate to present a smaller profile. It's a delicate balancing act performed automatically by the station's thermal control computers, adjusting continuously as the station orbits Earth and as power consumption varies with crew activities. Astronauts aboard the station experience a carefully controlled environment. Interior temperatures are maintained between 18 and 27 degrees Celsius, a comfortable range despite the wild extremes just centimeters away beyond the hull. This climate control is essential not just for comfort, but for survival and equipment function. Electronics have specific temperature ranges where they operate reliably. Batteries can fail if too cold or too hot. Experiments often require precise temperature control. The station is a bubble of warmth and life in an environment that would quickly kill any unprotected living thing. Future missions will face even greater thermal challenges. NASA's Artemis program aims to return humans to the Moon by the mid-2020s, establishing a sustainable presence, including a lunar gateway station in orbit and eventually a surface base. The Moon's environment is thermally harsh, with temperature swings we mentioned earlier, ranging from 127 degrees Celsius in sunlight to -173 degrees Celsius in shadow. Unlike the International Space Station, which orbits in relative thermal equilibrium with frequent day-night cycles, a lunar surface base will experience 14 Earth days of continuous sunlight, followed by 14 days of continuous darkness. Engineers are developing innovative solutions. One approach uses regolith, lunar soil, as insulation. By covering habitats with meters of regolith, you can buffer against the temperature extremes and also provide radiation shielding. Another approach involves locating bases in permanently shadowed craters near the lunar poles. where temperatures remain relatively constant at around -240 degrees Celsius. This sounds counterintuitive. Why choose one of the coldest places on the Moon? But constant cold is easier to manage than wild swings, and these polar regions may contain water ice, an invaluable resource for future explorers. The thermal challenges of Mars are different but no less demanding. Mars has a thin atmosphere, mostly carbon dioxide, at about 600 pascals pressure, less than 1% of Earth's. This atmosphere provides minimal insulation, so temperature swings are large, but not as extreme as the airless Moon. The atmosphere also allows for some convective heat transfer, which actually complicates thermal design. Engineers must account for conduction, convection, and radiation, making Mars' thermal systems more complex than those for the Moon. SpaceX's Starship, designed for Mars missions, will need sophisticated thermal protection for atmospheric entry and climate control for the months-long journey and surface stay. The spacecraft will experience the searing heat of atmospheric entry, thousands of degrees Celsius on its heat shield, then the cold of the Martian surface. Keeping crew and cargo within safe temperature ranges throughout this journey requires engineering that pushes the boundaries of current technology. Beyond Mars, the thermal challenges become truly extreme. Europa, Jupiter's ice-covered moon, has surface temperatures around -160 degrees Celsius, yet beneath its frozen crust lies a liquid ocean kept warm by tidal heating from Jupiter's gravitational pull. A mission to explore Europa's ocean, such as the proposed Europa Clipper or a future lander, would need to survive some of the coldest surface conditions in the solar system while potentially accessing one of the warmest and most habitable environments beyond Earth. Saturn's moon Titan presents a different extreme. With surface temperatures around -179 degrees Celsius, it's cold enough that water ice is as hard as rock, and methane exists as a liquid, forming lakes and seas on Titan's surface. The Cassini-Huygens mission's Huygens probe, which landed on Titan on January 14, 2005, had to be designed to operate in these cryogenic conditions. Its batteries and electronics were carefully insulated and heated to maintain functionality long enough to transmit data from the surface. What Huygens discovered was a world of exquisite strangeness. Methane rain falls from organic haze layers. Liquid methane and ethane flow in rivers and collect in lakes. Cryovolcanoes may erupt with water-ammonia mixtures instead of molten rock. It's a hydrological cycle like Earth's, but with temperatures so low that the working fluid is methane instead of water. Understanding Titan requires understanding how chemistry and physics work at temperatures just 94 Kelvin above absolute zero, where familiar substances behave in alien ways. Scientists studying Titan are essentially learning a new kind of planetary science, one where methane plays the role water does on Earth, and where water ice forms mountains and bedrock. This isn't just academic curiosity. If life can exist in Titan's methane lakes, or in Europa's subsurface ocean, or in the ammonia water oceans potentially existing inside other icy moons, then life is far more adaptable to cold than we've imagined. The cold of space may not be a barrier to life, but merely a different environment where biology could find a way. Astrobiologists are increasingly interested in these cold environments. On Earth, life exists in surprising places: Antarctic ice, Arctic permafrost, deep-sea hydrothermal vents. Microbes called psychrophiles, cold-loving organisms, thrive at temperatures near freezing. Some bacteria can remain viable when frozen for millions of years, reviving when conditions improve. If Earth life can adapt to such extremes, why couldn't life elsewhere adapt to the cold of Europa's ocean or the methane lakes of Titan? The question of extraterrestrial life brings us back to temperature in a fundamental way. Life as we know it requires liquid water, which exists only in a narrow temperature range, 0 to 100 degrees Celsius at Earth's atmospheric pressure, slightly wider at different pressures. The habitable zone around a star, the region where liquid water can exist on a planet's surface, is defined primarily by temperature. Too close to the star, water boils away. Too far, it freezes. Earth sits comfortably in the Sun's habitable zone, but so might other worlds around other stars. Astronomers have discovered thousands of exoplanets, planets orbiting stars other than the Sun. Many lie within their stars' habitable zones. Proxima Centauri b, orbiting the closest star to our solar system just 4.24 light-years away, might have surface temperatures allowing liquid water. Kepler 442b, 560 light-years away, is considered one of the most potentially habitable exoplanets found. TRAPPIST-1e, F, and G, 3 planets in a system 39 light-years distant, all orbit within their star's habitable zone. Each of these worlds has a temperature profile determined by its distance from its star, its atmosphere, and its geological activity. But determining actual surface temperatures of exoplanets is incredibly difficult. We can estimate based on stellar radiation and orbital distance, but atmospheres complicate everything. Venus receives less solar radiation than Earth, yet its surface is hot enough to melt lead, about 470 degrees Celsius, because of a runaway greenhouse effect. A thick carbon dioxide atmosphere traps heat, making Venus the hottest planet in our solar system, despite being farther from the Sun than Mercury. An exoplanet in the habitable zone could have a similar thick atmosphere and be entirely uninhabitable, or it could have no atmosphere and be frozen despite adequate stellar radiation. The James Webb Space Telescope, launched on December 25, 2021, is revolutionizing our ability to study exoplanet atmospheres. By observing the infrared spectrum of starlight passing through or reflecting off an exoplanet's atmosphere, Webb can detect molecules like water, carbon dioxide, and methane and estimate atmospheric temperatures. In 2023, Webb detected carbon dioxide in the atmosphere of WASP-39b, a gas giant orbiting a star about 700 light-years away. It also observed TRAPPIST-1b and found it likely has no significant atmosphere. Each observation refines our understanding of how temperature, atmosphere, and habitability connect. Temperature also affects how we search for life. The radiation spectrum of an object depends on its temperature. Planets, being much cooler than stars, emit primarily in infrared wavelengths. To detect them, we need infrared telescopes. The cosmic microwave background, cooled to 2.7 Kelvin, peaks at microwave wavelengths around 1 millimeter. Molecular clouds at 10 Kelvin emit at millimeter and sub-millimeter wavelengths. The universe reveals different aspects of itself depending on what temperature range you observe. This is why astronomers build different kinds of telescopes. Optical telescopes observe hot objects, stars, nebulae heated by stars, galaxies filled with stars. X-ray telescopes observe very hot objects, gas in galaxy clusters, the environments around black holes, stellar coronae. Infrared telescopes observe cool objects, planets, brown dwarfs, dusty star-forming regions. Radio telescopes observe cold objects, molecular clouds, the cosmic microwave background, and also non-thermal radiation from energetic processes. Each wavelength regime is a different thermometer, measuring the universe's temperature structure across vastly different scales. The coldest object ever detected in space is the Boomerang Nebula, which we mentioned earlier. It's about 5,000 light-years from Earth in the constellation Centaurus. Measurements show regions as cold as 0.5 Kelvin, just half a degree above absolute zero, colder than the cosmic microwave background. How is this possible? The nebula is created by a dying star expelling its outer layers at high speed. As this gas expands, it cools adiabatic, the same principle that makes compressed air cans cold when you use them. The expansion is so rapid that the gas cools below the background temperature of space. Eventually, the Boomerang Nebula will warm back up as it absorbs radiation from the cosmic microwave background and nearby stars. The universe is filled with this 2.7 Kelvin radiation, so nothing can remain colder than that for very long unless it's actively cooled. The Boomerang Nebula represents a temporary dip below the universe's ambient temperature, a refrigerator in space powered by the dying gasps of a star. In a few thousand years, it will equilibrate with its surroundings and be just another planetary nebula at the background temperature. This raises an interesting point about equilibrium. Everything in space is slowly coming into thermal equilibrium with the cosmic microwave background. Stars fight against this by generating energy through fusion, maintaining high internal temperatures. But eventually, even the longest-lived stars will exhaust their fuel. Planets and moons cool gradually, radiating away their primordial heat and the heat generated by radioactive decay. Black holes emit Hawking radiation, though at temperatures far below the current cosmic background, so they actually absorb more energy than they emit and will continue to do so until the universe cools below their temperature. The timeline for the universe's thermal evolution is staggering. Currently, at 13.8 billion years old, the universe is still relatively young and vibrant. Stars are forming, galaxies are colliding, black holes are growing. The cosmic microwave background is 2.7 Kelvin and cooling. In another trillion years, the universe will be about 70 times older than it is now, and the background temperature will have dropped to about 0.04 Kelvin. Most stars will have died, galaxies will have used up most of their gas, and star formation will have nearly ceased. By the time the universe is 10 to the power of 14 years old, about 7,000 times its current age, the last stars will be dying. Only the lowest mass red dwarfs will still be shining, feeble embers in an increasingly dark cosmos. The background temperature will be immeasurably small, a tiny fraction of a Kelvin. From that point forward, the universe becomes increasingly cold and empty, a vast dark expanse where isolated stellar remnants, white dwarfs, neutron stars, and black holes drift in the darkness. But even this isn't the end of the thermal story. White dwarfs, the dense remnants of stars like our Sun, start at temperatures of tens of thousands of Kelvin and cool gradually. They have no internal energy source, so they simply radiate away their heat over trillions of years. Eventually, they become black dwarfs, crystalline spheres of carbon and oxygen at temperatures approaching the cosmic background. The universe isn't old enough yet for any black dwarfs to exist. The oldest white dwarfs, formed from the first stars in the universe, are still warm, still radiating detectable heat. The first black dwarfs won't form for another 10 trillion years or so. Neutron stars follow a similar path. They form hot, with core temperatures exceeding 1 billion Kelvin, but cool through neutrino emission and thermal radiation. Within 10 million years, a neutron star's surface temperature drops to around 1 million Kelvin. After 1 billion years, it might be 10,000 Kelvin, still hot by everyday standards, but cooling toward the background. Eventually, neutron stars too will become dark, cold objects detectable only by their gravitational influence. Black holes present the most interesting long-term thermal scenario. They absorb matter and radiation, growing larger and colder. A stellar mass black hole has a temperature measured in billionths of a Kelvin. So in today's universe, it absorbs cosmic microwave background radiation faster than it emits Hawking radiation, and it actually grows colder as it grows larger. But as the universe expands and cools, eventually the background temperature will drop below even these tiny temperatures. At that point, black holes will begin to evaporate through Hawking radiation. The evaporation process is extraordinarily slow for large black holes. A black hole with the mass of the Sun would take about 10 to the power of 67 years to evaporate completely. A supermassive black hole like the one at our galaxy's center, with a mass of about 4 million times the Sun, would take about 10 to the power of 99 years. These timescales are so vast they defy comprehension. The current age of the universe is only 10 to the power of 10 years, 4.4 billion in scientific notation. We're talking about timescales that are 1 trillion trillion times longer than the universe's current age. Yet the mathematics of thermodynamics insists that black hole evaporation must eventually occur. As a black hole evaporates, it becomes smaller and hotter. The temperature increases inversely with mass, so as mass decreases, temperature rises. In its final moments, a black hole becomes intensely hot and explodes in a burst of radiation. This final explosion would briefly create one of the hottest objects in the universe, a spectacular end to an entity defined by its gravitational power. But that explosion lies so far in the future that the universe it occurs in would be unrecognizable to us, a cold, dark, nearly empty expanse, where such an event would be an extraordinary anomaly. This cosmic thermal evolution connects to deep questions about the nature of time and existence. The second law of thermodynamics, which states that entropy always increases, gives time a direction. We remember the past but not the future because the past has lower entropy than the present, and the present has lower entropy than the future. The universe started in a low entropy state, the hot, dense Big Bang, and has been increasing in entropy ever since. The cooling of the universe, the formation and death of stars, the evaporation of black holes, all of these processes increase total entropy. Some physicists speculate about whether the universe could somehow restart, whether quantum fluctuations in the far future could create a new Big Bang, beginning the cycle again. Others propose that our universe might be one of many, a multiverse, where different regions have different physical laws and different thermal histories. These ideas push the boundaries of testable science, venturing into philosophy and speculation, but they all start from the same foundation: observations of temperature, entropy, and the expansion of space. Temperature measurements have given us the age of the universe. By precisely measuring the cosmic microwave background temperature and its tiny fluctuations, cosmologists determined that the universe is 13.8 billion years old, plus or minus about 20 million years. That's an astonishing level of precision, achieved by measuring the temperature of ancient light to within thousandths of a Kelvin. The Planck satellite, which operated from 2009 to 2013, measured the cosmic microwave background temperature as 2.7255 Kelvin, with uncertainty in the fourth decimal place. These tiny temperature fluctuations, deviations of only a few millionths of a Kelvin from the average, reveal the seeds of cosmic structure. Slightly warmer regions had slightly higher density in the early universe. Gravity amplified these density variations over billions of years, eventually creating the galaxies, clusters, and vast cosmic web we see today. Everything around you, the Earth, the Sun, our galaxy exists because of quantum fluctuations in the first fraction of a second after the Big Bang that left tiny temperature imprints in the cosmic microwave background. This brings us full circle to where we started. The question, how cold is space, seemed simple, but the answer has taken us through the entire history and future of the universe, from the Big Bang to the heat death, from quantum mechanics to cosmic evolution, from spacecraft engineering to the search for extraterrestrial life. Temperature in space isn't just a number. It's a fundamental parameter that shapes everything we see, everything we are, and everything that will ever exist. Space is cold, 2.725 Kelvin on average, but it contains regions of extreme heat and even colder regions. It's an excellent insulator that paradoxically allows enormous temperature gradients to exist side by side. It's a laboratory where we can study physics in conditions impossible to replicate on Earth. It's an environment that challenges human technology and ingenuity every time we venture beyond our atmosphere. And it's a cosmic thermometer recording the age and evolution of the universe itself. For astronauts and spacecraft designers, the cold of space is an engineering problem to be solved with insulation, heaters, and thermal management systems. For astronomers, it's a tool for understanding the cosmos, with different temperatures revealing different aspects of cosmic structure. For physicists, it's a window into fundamental laws governing energy, entropy, and the flow of time. For astrobiologists, it's a factor determining where life might exist beyond Earth. And for all of us, it's a reminder of how extreme and alien the universe beyond our blue marble planet truly is. The practical implications of space's temperature have shaped every aspect of space exploration. Consider the spacesuits worn by astronauts during spacewalks, or extravehicular activities as NASA formally calls them. These suits are miniature spacecraft designed to protect humans in an environment where temperature swings between extremes. The extravehicular mobility unit used on the International Space Station has multiple thermal control layers. The innermost layer is a liquid cooling and ventilation garment, essentially underwear, with thin tubes woven throughout. Water circulates through these tubes, carrying heat away from the astronaut's body to a sublimator, where it evaporates into space. Cooling the water that continues circulating, this might seem wasteful, venting precious water into the vacuum, but it's remarkably efficient. The phase change from liquid to gas absorbs enormous amounts of heat, about 2,250 joules per gram of water at 0 degrees Celsius. During a typical 6-hour spacewalk, an astronaut might use about 3.6 kilograms of water for cooling. That water, now vapor, disperses into space and freezes into tiny ice crystals that drift away, each crystal carrying a small amount of the astronaut's body heat into the cosmos. The outer layers of the spacesuit provide insulation and protection. Multiple layers of aluminized mylar and other materials reflect thermal radiation, both incoming from the sun and outgoing from the astronaut's body. White outer fabric reflects visible and infrared light, keeping solar heating to a minimum. Depending on whether the astronaut is in sunlight or shadow, different thermal challenges arise. In sunlight, preventing overheating is the priority. In shadow, preventing excessive cooling becomes important. The suit's thermal control system adjusts automatically, balancing heat generation from the astronaut's metabolism against heat gain from the sun and heat loss to space. The gloves present a particular challenge. Hands need dexterity, so gloves can't be too bulky, yet they must protect against temperature extremes and the vacuum. Astronauts often report that their fingertips get cold during spacewalks, despite heating elements built into the gloves. The challenge is dissipating heat from working muscles in the hands while protecting fingertips that generate less heat and have greater surface area for heat loss. It's a microcosm of the larger thermal management problem. Different parts of a system have different thermal needs, all of which must be balanced simultaneously. Future spacesuit designs are becoming more sophisticated. NASA's Exploration Extravehicular Mobility Unit, being developed for Artemis lunar missions, incorporates advanced thermal control for the more extreme lunar environment. The Moon's regolith, soil, has very low thermal conductivity, so it heats up intensely in sunlight and cools dramatically in shadow. Astronauts walking on the lunar surface will kick up dust that could coat their suits, changing thermal properties. The suit must adapt to these changing conditions while maintaining a comfortable interior environment. On the Moon, astronauts will also face extended surface stays, potentially weeks at a time during later Artemis missions. Thermal control for habitats becomes crucial. Lunar habitats must maintain comfortable temperatures while minimizing power consumption. One innovative approach being studied involves heat pumps that move heat from one side of a habitat to another. During the lunar day, excess heat is stored in thermal mass, perhaps water tanks or regolith. During the lunar night, this stored heat is released, supplemented by electrical heaters as needed. It's essentially a giant thermal battery, capturing heat when abundant and releasing it when needed. Mars habitats will face different challenges. The thin atmosphere allows some convective heat transfer, but not much. Dust storms can last for months, reducing solar power availability precisely when heating is most needed. The InSight lander, which operated on Mars from November 2018 to December 2022, experienced this firsthand. As dust accumulated on its solar panels, power generation dropped and the spacecraft had to conserve energy. Eventually, it couldn't generate enough power to keep warm and operate simultaneously, leading to mission end. Future Mars missions will likely use nuclear power sources, both for electricity and heat. Radioisotope thermoelectric generators, which convert heat from radioactive decay into electricity, have powered missions from the Apollo lunar seismometers to the Perseverance Mars rover. They provide consistent power regardless of sunlight and generate waste heat that can warm spacecraft components. For a crewed Mars mission, a small nuclear reactor might provide the substantial power needed for life support, heating, oxygen production, and other systems. Managing the reactor's heat becomes a thermal control challenge in itself, requiring radiators to dissipate waste heat that can't be used productively Venturing beyond Mars, toward the outer solar system, temperatures drop dramatically and thermal challenges intensify. Jupiter receives only 4% of the sunlight intensity that Earth does. Saturn receives 1%. At Neptune's distance, sunlight is 900 times fainter than at Earth. Solar panels become increasingly ineffective, and radioisotope power sources become necessary. But these generators produce heat continuously, and in the outer solar system's cold, this becomes an asset rather than a liability. The waste heat from a radioisotope power source can keep spacecraft systems warm without additional heaters. The Voyager spacecraft, launched in 1977 and now traveling through interstellar space beyond our solar system, demonstrate this beautifully. Each Voyager carries 3 radioisotope thermoelectric generators producing about 470 watts at launch, about 250 watts today as the plutonium-238 fuel decays. This power runs the spacecraft systems and provides heat. Even now, more than 45 years after launch and over 20 billion kilometers from the Sun, the Voyagers maintain temperatures warm enough for their electronics to function. They're tiny bubbles of warmth, powered by nuclear decay, drifting through the interstellar medium where temperatures approach the cosmic background of 2.7 Kelvin. Voyager 1 crossed into interstellar space in August 2012, and Voyager 2 followed in November 2018. They're the most distant human-made objects, experiencing an environment no spacecraft had entered before. The temperature of interstellar space is essentially the cosmic microwave background temperature, with slight variations depending on local conditions. The spacecraft occasionally detect small increases in temperature as they pass through the boundaries of solar eruptions that have propagated outward through the solar system and into interstellar space. These temperature variations, though minute, provide valuable data about the interaction between the solar wind and the interstellar medium. The temperature structure of the interstellar medium itself is complex and fascinating. It's not uniform. Regions of different density and temperature coexist, from cold molecular clouds at 10 Kelvin to warm ionized regions at 8,000 Kelvin to hot coronal gas at 1 million Kelvin. These regions occupy different volumes, with the hot gas filling the most space but containing relatively little mass. The cold clouds are dense and compact, the birthplaces of stars, while the hot gas is tenuous, filling vast volumes but containing only scattered atoms. Supernova explosions drive much of this structure. When a massive star explodes, it releases more energy in a few seconds than the Sun will emit in its entire 10 billion year lifetime. This energy heats surrounding gas to millions of Kelvin, creating expanding bubbles of hot plasma. These bubbles eventually cool and dissipate, but while they exist, they dominate the local thermal structure. Multiple supernovae in the same region can create superbubbles hundreds of light years across. Our solar system sits inside one such bubble, called the local bubble, created by supernovae over the past 10 to 15 million years. The local bubble is about 1,000 light-years across, with gas at a temperature of around 1 million Kelvin, but at extremely low density. Despite being so hot, this gas wouldn't feel warm if you could somehow be immersed in it. Temperature and heat are different things. Temperature measures the average kinetic energy of particles, while heat measures total thermal energy. In the near vacuum of the local bubble, there are so few particles that even though each one is moving incredibly fast, the total thermal energy is minuscule. You'd freeze from radiative heat loss long before the sparse hot atoms could transfer significant energy to you. This distinction between temperature and heat is crucial for understanding space. The thermosphere of Earth's atmosphere at altitudes above 80 kilometers can reach temperatures of 1500 Kelvin during solar maximum. Yet spacecraft and satellites in the thermosphere don't experience this temperature directly because the air is too thin to transfer much heat through conduction or convection. The International Space Station orbits in the thermosphere, where atmospheric temperature can exceed 1000 Kelvin, yet the station's thermal control system focuses primarily on radiative heat transfer from the Sun, not the sparse hot atmosphere around it. This same principle explains why a comet's tail doesn't melt the comet. When a comet approaches the Sun, solar radiation heats its surface, vaporizing ice and creating the characteristic tail. But the tail, though it can extend millions of kilometers and contain gas heated to thousands of Kelvin, is so diffuse that it transfers negligible heat back to the comet nucleus. The nucleus remains cold, typically well below freezing even when relatively close to the Sun, because the vacuum of space prevents convective heat transfer, and the comet's surface reflects or re-radiates much of the incoming solar energy. Understanding these thermal principles has practical applications for asteroid mining and resource utilization, concepts that are moving from science fiction toward reality. Companies are developing plans to mine asteroids for water, metals, and other resources. The thermal environment of an asteroid presents unique challenges. Asteroids have no atmosphere, so their surfaces experience wild temperature swings between sunlight and shadow. The asteroid Bennu, visited by NASA's OSIRIS-REx mission from 2018 to 2021, has surface temperatures ranging from about -73 degrees Celsius in shadow to over 127 degrees Celsius in sunlight. Mining equipment on an asteroid would need to function across this temperature range or operate only during certain thermal conditions. Extracting water ice from a permanently shadowed crater would require heating the ice to vaporize it, then capturing and condensing the vapor, all while managing the extreme cold of the surroundings. Processing metals would require different thermal management, potentially using concentrated solar energy for smelting while preventing heat loss to the cold environment. Every operation becomes a thermal engineering challenge. The same applies to in-situ resource utilization on the Moon or Mars. NASA's plan for sustainable lunar exploration includes extracting oxygen from lunar regolith, which is about 45% oxygen by mass, chemically bound in minerals. The extraction process requires heating regolith to high temperatures in reactors, then capturing the released oxygen. This must happen in an environment where external temperatures swing by 300 degrees Celsius between day and night. The energy requirements are substantial, and managing the thermal balance of the process, capturing waste heat for other uses while preventing overheating of critical components, becomes essential for efficiency. These practical considerations connect to the broader question of human expansion beyond Earth. If we're to become a spacefaring civilization, establishing permanent settlements on other worlds or in space habitats, we must master thermal management at every scale. From individual spacesuits to habitats to industrial facilities, to eventually terraformed environments, temperature control is fundamental. Understanding how cold space is and how heat behaves in vacuum isn't just academic knowledge. It's practical engineering that will determine whether humans can thrive beyond Earth. Looking back at our journey through this question, we've explored temperature from the quantum scale to the cosmic scale, from the coldest laboratories on Earth to the hottest stars, from the beginning of the universe to its far future. We've seen that space's temperature is both simple and complex, both uniform and varying, both a deadly hazard and a manageable engineering challenge. The cosmic microwave background provides a baseline temperature of 2.725 Kelvin throughout the universe, but local conditions create enormous variations around this average. Space is cold in the sense that most of it is near absolute zero, but it contains pockets of intense heat wherever stars burn and matter collides. It's an excellent insulator, allowing extreme temperature gradients to exist side by side. It's a laboratory revealing physics impossible to study on Earth. And it's our frontier, the environment we must understand and adapt to if we're to explore beyond our home world. The coldness of space shaped the universe we inhabit. The cooling after the Big Bang allowed matter to form, then atoms, then the first stars and galaxies. The temperature of the cosmic microwave background carries information about the universe's age, composition, and geometry. The thermal death predicted by thermodynamics gives time a direction and the universe an ultimate fate trillions of years hence. Temperature isn't just a property of space, it's a fundamental parameter woven into the fabric of cosmic existence. For us as individuals living on Earth's surface, the cold of space is remote, something we'll likely never experience directly, but its effects surround us. The satellites providing communications, navigation, and weather data all manage the thermal challenges of space. The astronauts aboard the International Space Station live and work in an environment just centimeters from the cold of space, kept alive by sophisticated thermal control systems. The observations of distant galaxies and exoplanets come from telescopes that must be cooled to cryogenic temperatures to function. Space's temperature, though distant, touches our lives in countless ways, and perhaps, for some watching this, the cold of space represents a personal frontier. Future astronauts, engineers, scientists, and explorers will face these temperature extremes directly. They'll don spacesuits and venture into environments where sunlight and shadow mean the difference between boiling and freezing. They'll design the next generation of spacecraft, habitats, and technologies that make human presence in space sustainable. They'll explore worlds so cold that nitrogen liquefies or so hot that lead melts, expanding the boundaries of human knowledge and capability. The question, how cold is space, has no single answer because space isn't a single thing. It's a vast continuum of environments, each with its own thermal character, from the nearly absolute zero of intergalactic voids to the billion Kelvin of stars. Understanding this thermal landscape is understanding the universe itself in all its magnificent extremes. Space is as cold as the aftermath of creation and as hot as the cores of dying stars. It's both the coldest and the hottest thing we know, a testament to the universe's astonishing range and our growing ability to measure, understand, and perhaps one day truly inhabit the cosmos beyond Earth. If the extreme temperatures of space fascinate you, click the video on the screen to see what happens when humans attempt century-long voyages through the void, the terrifying reality of generation ships. Discover why generation ships is humanity's most ambitious endeavor in interstellar space travel.